I'm going to draw a picture of something you saw a million times last year in your dynamics unit, towards the end of your dynamics unit. It's like a roller coaster, one of those roller coaster type problems, again, that we saw a million times. Maybe the speed of the roller coaster at the top of the hill is 0 meters per second. Maybe the height of the hill is 20 meters. And we want to find the speed at the bottom of the hill. We want to find the speed when the roller coaster has reached the bottom of the hill. Do you guys remember how to do that? VI is equal to VF? No, but you're close. Kind of close, at least. Something I is equal to something F. EI is equal to EF. Yeah, the energy initial is equal to the energy final. What law was it that dictated that the energy initial was equal to the energy final? And we talked earlier in the year about the law of conservation of charge and the law of conservation of momentum. This is, yeah, it's the law of conservation of energy. You guys remember that? EI is equal to EF. What kind of energy do you have at the top of this hill at the beginning of this problem? Potential energy, and that's going to be MGH, right? Is there any kinetic at the beginning of this problem? No, there would be if it was moving, right? We'd say MGH plus 1/2 mv squared if it was moving, but in this case, there's not. There's just potential because it just has a height. What's the final energy at the bottom of the hill equal to? Let's assume, by the way, that 20 meters goes all the way to the bottom. Wasn't drawn very well. How much final energy do we have, or what kind of final energy do we have? Kinetic, it's moving, right? Is there any potential at the bottom? No. I mean, at some point there could be, right? It depends upon how far down the hill it's gone, but in the end, this is at the bottom of the hill. There is no potential because there is no height. Does that ring a bell? That's not exactly what we're going to do today, but it's close to what we're going to do today. Today we're going to talk about conservation of energy in the context of electric charges, not in the context of masses going down hills. So let me draw another picture now. Let's say we have two charged plates. First one is positive, and the second one is negative. We have a positive charge right here in that electric field. It's going at 0 meters per second. We have a potential difference across these plates of 20 volts. What's going to happen to that charged particle as a result of that positive plate and as a result of that negative plate? In other words, as a result of the electric field. What's going to happen to it? William? It's going to shoot to the other side. Specifically, it's not just going to move to the other side, it's going to accelerate to the other side, just like the car accelerated down the hill. The car accelerates down the hill in a downward gravitational field. The charge accelerates, for lack of a better term, down the hill in a downward electric field. What kind of energy do you think that this charge might have before it accelerates? What kind of energy does anything need before it accelerates? Potential. But it's not going to be gravitational potential, right? It's going to be electric potential. We'll talk about what equation represents that in just a moment here. Hey, we start off with electric potential energy. What kind of energy do we finish off with at the end of it? When it reaches the other side, when the positive charge gets to the other plate, which is equivalent to the bottom of the hill. It's got kinetic energy, right? Just like the car goes from potential to kinetic energy as it speeds up, the charge goes from potential to kinetic energy as it speeds up. Now, we're not going to put in MGH here. We're going to put in Q times V. Remember the equation for electric potential? V is equal to E over Q. If the electric potential is E over Q, then potential energy, rearrange that, is Q times V. So electric potential energy, Q times VI, is equal to kinetic energy, 1/2 mvf squared. So it's exactly the same thing, except that we're subbing in QV wherever we had MGH. What if we introduced a speed here? What if it was going not at 0 meters per second, but at 10 meters per second? How would this change? How would the first problem, that is, change? Paige? Right. So we'd say MGH plus 1/2 mvi squared. The initial energy is kinetic and potential. How would it change if this charge right here was given an initial speed? 10 meters per second probably isn't a realistic speed for the speed of a charged particle between two parallel plates, but we'll go with that just for comparison purposes here, okay? It's got an initial speed of 10 meters per second. How would it change the EI equals EF for this one? Same thing, right? It would be potential plus kinetic, the only difference being that the potential is QV instead of MGH. All right, what if now I want to find the speed of the car halfway down the hill? We haven't changed anything at the beginning. We still have potential and kinetic at the beginning of the problem because we still have a height and we still have a speed. But what do we have at the end of the problem? What do we have at EF now, Mac? We've got potential and kinetic as well. So it's going to be 1 FMV squared, 1 FMVF squared, plus mg HF. Make sense? What would the value of HF be? What would the value of HI be? What would this one be right here? 20 volts, or sorry, 20 meters, right? And what would HF be? Assuming we're trying to find the speed halfway down, HF would be 10. All right, well, let's change this one. Now we're not trying to find the speed of this positive particle all the way down when it's reached the other plate, the equivalent to the bottom of the hill, but rather we're trying to find the speed of it halfway across this potential difference. What do we start off with? Still potential and kinetic as we did right here. And what do we end off with? Kinetic, because it's moving now, plus potential. But potential this time isn't MGH, potential is QV, QVF in this case. What would VI be right here? What would VI be? 20 volts. What would VF be? 10 volts, because we've gone halfway across. Does that make sense, guys? Yeah, go ahead. Yes, yes, yeah. Potential energy is always measured, right, Maddie? Relative to something. And we can choose. We can always choose what it's relative to. Okay, we've chosen in this question, like we usually do, relative to the bottom of the hill. Okay, but we don't have to do that. Okay, doing a question like this, we could choose it relative to this, which makes VI 10 and would make VF 0, right? Same thing over here. We could make, not VI and VF, but HI and HF, right? HI would be 10 and HF would be 0 if we define this as our 0 point. Okay, we could define this as our 0 point as well, where VI would be 10 and VF would be 0. Okay. Most people get a little troubled by that, though. Okay, most people would rather just define it relative to the bottom. Just means an extra term into the equation. But listen, if that makes it a little bit easier for us, then that's what we should do. So whatever works for you. Okay, whatever works for you. Today we're going to focus on these problems where charged particles are accelerating in electric fields. Every time you see a charged particle accelerating in an electric field, speeding up in an electric field, I want you to think of it as a car accelerating in a gravitational field. In other words, I want you to picture every single problem where a charge is accelerating in an electric field as a car going down a hill. When a car goes down a hill, listen, we can solve these problems easily, right? Okay? We know these problems like the back of our hand. It's easy. Okay? MGH is equal to 1/2 mv squared, or MGH plus 1/2 mv squared, and so on, right? We can solve these problems easily. So if we can solve these problems easily, then I want you to think of these problems in exactly the same way. Because if that's the case, solve these easily, then we should be able to solve these ones easily as well. All we're going to do is, again, picture this as a car going down a hill, MGH equals 1/2 mv squared, whatever, but then sub in QV wherever we have MGH. That make sense? What if the car was going up the hill? What if you got a car right here with a certain speed, 10 meters per second, and the car is going up the hill? Let's say the height of the hill is 20 meters, and we want to find out how fast the car is moving when it reaches the top of the hill. What do you do in that case? It's not much different, is it? Still EI equals EF. Whenever we have this roller coaster car changing height, we say EI equals EF. But what kind of energy do we have at the beginning of this problem? It's kinetic this time, right? Not potential. It's kinetic. So instead of being a conversion of potential to kinetic, it's going to be a conversion of kinetic to potential. What kind do we have at the end of the problem? Potential, because it's got a height, and looks like it's still moving, so it's got kinetic there as well. Just a kinetic energy that's less than the original kinetic energy. Well, what about this one? Let's draw this a little bit differently this time. Doesn't matter whether it's vertical. Okay, I drew these parallel plates vertical here. It was going down toward the bottom plate. It could easily be going up or sideways. It doesn't matter. If it's speeding up, it's like a car going down a hill. It doesn't matter which way it's going. Okay, here we're going to say that it's slowing down. We got a positive particle right here with an initial speed of 10 meters per second. Okay, again, that's probably too low of a speed, but we'll just use it for comparison purposes. A potential difference of 20 volts. How would we analyze this? Well, what's going to happen to this positive particle? Speed up or slow down? It's going to slow down, right? So it's like a car going up a hill. It's going to slow down. We say EI equals EF. Well, when a car goes up a hill, it starts with kinetic energy. Has to, otherwise it's not going to go up a hill. Same thing here. What kind does it end up with? Potential energy and kinetic energy. Except we're going to sub QV wherever we see MGH. So again, same problem really. Same problem. It's just we're subbing QV wherever we see MGH. Whenever you see a charged particle speeding up, always think a car going down a hill. Wherever you see a charged particle slowing down, always think a car going up a hill. And solve it that way. Okay, solve it that way. Make it easy. Turn a problem that you can't visualize, that you can't see. Okay? I know for me, in my mind, I can't see a charged particle speeding up in an electric field. I can see a car speeding up as it goes down a hill. It's a lot easier for me to visualize. So that's the way I treat it. It makes the problem a lot easier for me. Make sense? All right, I've got a few things written down here, but in the end, guys, I'm going to let you use your judgment as to what you write down for this. If you've written down and made a couple notes about the stuff that I've put on the board already, then that's probably pretty good, because in the end, that explains what we're going to explain here. This is just kind of doing all that stuff in words as opposed to in example or in demonstration. Basically, what we're saying here is that a charged particle speeding up is like a car going down a hill. Potential energy is converted to kinetic energy. When a charged particle slows down, it's like a car going up a hill, where we have kinetic energy being converted to potential energy. Okay, we may have kinetic and potential energy at the beginning. We may have kinetic and potential energy at the end. In the end, we may only have one of those types of energy on each side, kinetic or potential. What you got to do is, again, look at it like the car. Okay, if it's speeding up, we know we have potential at the beginning. We know we have kinetic at the end. If it starts with a speed, well, then we also have kinetic at the beginning. Okay, if it hasn't made it to the bottom of the hill, well, then we also have potential at the end. So what's really the only difference between these problems that we're doing now and the problems that we did last year? Again, we're subbing in QV wherever we had MGH. So let's replace MGH with QV. Remember, that V is a capital V, right? It's not speed, it's electric potential, the energy per unit charge, a term that we talked about a couple of days ago. All right, let's take a look at our last type of problem that we're going to do this unit before our test. A couple of them. First one is 11.10 on page 571. It says a pith ball. Pith ball is just this really light material. It's made from the inside of a plant. It's good with the electrostatics because it's really, really light. So if it has an electric charge on it, if it experiences an electric force, it moves really easily. Okay, so that's what a pith ball is. Pith ball with a mass of 2.4 times 10 to the negative 4 kilograms has a positive charge of 1.2 times 10 to the negative 8 coulombs. It's initially at rest at location A. At this location, it has this much potential energy. When it's released, it accelerates. Position B, it has this much potential energy. What's the speed of the ball when it reaches position B? So you may not know when you read this question immediately where to start with it. But in the end, let's go back to basic principles. I said a few minutes ago, when a charged particle speeds up, we're going to do conservation of energy. A charged particle is speeding up here. We don't know what it speeds up from. Well, we know it goes from rest, I guess. We don't know what the final speed is. That doesn't matter. We know that it speeds up. So let's think of it as a car going down a hill. When a car goes down a hill, we say EI is equal to EF. What kind of energy must the car have at the top of the hill? It's got potential energy, right? MGH. Now, bear with me for a second. Okay, I'm going to write down MGH, even though we know that there's no gravitational potential here. Okay, so just hold on before you write this down. We start off with potential energy, top of the hill. Now, it says this charge is at rest, so the car at the top of the hill is at rest. Does it have kinetic energy? No, not if it's at rest, right? There's no kinetic energy. Now, the car is going down the hill. It's speeding up as it goes down the hill. So at the end of the problem, the car would have kinetic energy. Well, so would the charge. So would the charge have kinetic energy. The car in this case, though, would it have potential energy at the end of the problem or not? Well, has the car gone all the way down the hill? Here's the top of the hill. Here's the bottom of the hill. Has the car gone all the way down the hill? No. So if it's only gone part way down the hill, then it's going to have potential energy at the end of the problem as well. What are we going to do here? We're going to replace MGH with QV. Now, in all likelihood, guys, you're not going to show the step that I just showed and erased, right? You're going to go directly to this equation as opposed to putting in MGH. But I just want to make the point that it's exactly the same thing as the car going down the hill, except for that MGH is QV instead. Now, good news or bad news, it depends upon your perspective, I guess. Some people will get confused at this point because of what we're given, and some people are going to look at it and say, oh, well, they're doing me a favor, save me some work here. I don't need to multiply QV. I don't need to multiply QV together. Why not? Yep. Yeah, I already have the potential energy here. The initial potential energy, it tells me, is 3.0 times 10 to the negative 7 joules. So in this particular question, we could have actually gotten away with it even writing in QV. We could have just wrote in EP. Well, we want to find the speed at the end of it. Half times the mass of 2.4 times 10 to the minus 4 times VF squared plus, again, they're doing me another favor. The potential energy at the end of the problem is 1.5 times 10 to the negative 8. That's smaller than it was in the beginning. Does that make sense? Should it be smaller? Absolutely, it should be smaller, right? You just converted potential to kinetic energy. If something's sped up, it can't have more potential energy at the end than it does at the beginning. If something's sped up, it has more kinetic. Therefore, it must have less potential. So let's solve this now. Okay, let's pull out our calculator and do this as a group here. We're going to say 3 times 10 to the minus 7. We're going to subtract from that 1.5 times 10 to the minus 8. And we get 2.85 times 10 to the minus 7. Okay, let's multiply that by 2 now. Let's divide that by 2.4 times 10 to the negative 4. And then we're going to square root that. We get an answer for VF of 4.87 times 10 to the minus 2, or 4.9 times 10 to the minus 2 meters per second. You know what the biggest trouble people have with these questions is? It's not solving a question like this. The biggest trouble that people have with a question like this is actually recognizing that they have to do EI equals EF. Okay, once we see that it's an EI equals EF problem, usually we can do it because it's just like the car going down the hill. Okay, but a lot of people, for whatever reason, just look at this, say, I don't know what to do. I'm not sure. Okay, when a charged particle speeds up, do this. When a charged particle slows down, do this. Except it's the other way around, right? Car going up the hill instead. Does that make sense? All right, let's take a look at these two problems, please. Okay, and see what you can do with those, okay? All right, guys, let's take a look at question number 2 here. Okay, this one says a small sphere with a charge of -2 microcoulombs and a mass of 1.7 times 10 to the minus 3 kilograms accelerates from rest, okay, toward a larger positive charge. And the speed of the sphere just before it strikes the positive charge is 5.2 times 10 to the 4. How much electric potential energy did the negative charge lose? So this is a charge speeding up, right? When a charge speeds up, we treat it like a car going down a hill. When a car reaches the bottom of the hill, it has all kinetic energy, no potential energy. When this charge reaches the bigger positive charge, okay, it's like it's at the bottom of the hill. So it has all kinetic and no potential energy. So let's set it up here. We're going to say EI is equal to EF. This thing is speeding up. We start off always with potential energy. We would say if it was a car going down a hill, we would say MGH. Well, this time we're going to say it's QV because it's an electric charge instead. Now it starts at rest, so the initial kinetic energy would be 0. When our car reaches the bottom of the hill, what kind of energy does it have? Just kinetic energy, right? We're going to say 1/2 mv squared. Now, what are we looking for here? We're looking for the potential energy that's lost. How much potential energy did it lose? Well, let's try this. Let's not even write in QV here. Or if we did, let's erase it. Let's say EP, the initial potential energy, is equal to 1/2 mv squared. That's 1/2 of 1.7 times 10 to the minus 3 times VF, which is 2.0 times 10 to the 4 squared. We solve for that, we end up getting 2.3 times 10 to the 6 joules. What have we really solved for here? The final kinetic energy. But what's the final kinetic energy the same as? The initial potential energy. And what's the initial potential energy the same as? Well, if we end up with 0 potential, we started with 2.3 times 10 to the 6, then the initial potential energy is equal to the whatever we lost. Does that make sense? So really all we have to do here to solve this problem is solve for the initial potential energy. Hey, listen, if we had V, QV, okay, we just use that, Q times V, but we don't. We don't know what VI is, the initial potential. But that's okay, because if we can find the final kinetic, it's equal to the initial potential, which of course is also equal to the change in potential. Maddie, question? Okay, good point. Maddie just said, and there's probably a number of other you guys that were thinking the same thing. I thought it would still have potential energy at the end because it was just before. Okay. What they mean when they say just before is kind of at the moment that it strikes. I always get this in physics 20. It's a similar question. We talk about when something hits. What's its speed when something hits? And everyone says, oh, it's 0. What's the speed when it hits the ground? 0, right? No. Okay, what's the speed after it hits the ground? 0. When it hits the ground, it's not 0. The demonstration I always do in physics 20 is I always get somebody laying down up here, and then I always stand up on a desk with my hole puncher, and then I always threaten to drop the hole puncher on them. And I never do it, of course. Sometimes you might feel it. No, I never do it. Never even feel like it. The point of that is, like, look, would that hole puncher hurt when it hits? Yes, it would hurt when it hits. Why? Because it's moving when it hits. Okay? So we're saying here that essentially, what's its potential energy as, it says before, it really should say, kind of as it hits the ground. Okay? What's its, how much potential energy does it have left as it hits the ground? 0. Right? Or how much potential energy does it have left as the charge hits the positive charge, or when it reaches the positive charge? 0. Okay, so for all intents and purposes, when they say before, they mean just that instant before. basically when it has no potential left. All right. Let's try another one. Should make a wish for this one. It's 1111, right? Example 11.11. 572 says two vertical plates are connected to a DC power supply. Here, let's make this one a little bit bigger because I know that some of you are getting old and losing your eyesight and having a little bit of trouble seeing this. The electric potential between the plates is 2.0 times 10 to the 3 volts. There's a mass of this value with a positive charge. It's placed at the positive plate and released. It accelerates toward the negative plate. In other words, it speeds up. Determine the speed of the sphere when it reaches, or the instant before that it reaches, basically when it reaches, right? The negative plate. Ignore any gravitational effects. All right, what's happening to this charge? Okay, strip away everything and just look at one basic principle. This charge is doing what? It's accelerating. It's speeding up. That's like a car doing what? Going down a hill. Okay, when a car goes down a hill, we say EI is equal to EF. What kind of energy does the car have at the top of the hill? Always. It's got to start with this, otherwise it isn't going down a hill. Sorry? Right. It's got to have potential energy. Okay? Bear with me for a second. I'm just writing in MGH because, again, I want to illustrate the similarities here. Does it have kinetic energy at the top of the hill? Well, if the car is moving, it does. Is the car moving in this case, or is the charge moving in this case? It's placed at the positive plate and released. It's like a car being placed at the top of the hill and released. Is that moving? No, it is like 1 second later, but not at the very beginning. So there would be no kinetic at the beginning. Now, we want to find the speed of the sphere just as it gets to the negative plate. Have I reached the bottom of the hill? The negative plate is the bottom of the hill here, right? What kind of energy does the car have at the bottom of the hill? Kinetic energy. Well, all we're going to do here to make this different from the hill problem is replace MGH with QV. And again, I don't care if you write down MGH and scratch it out, or whether you just go straight to QV. Okay, I just want to show you that it's the same thing. Okay, we want to find the final speed here. We know the charge is 2.6 times 10 to the minus 12. And the initial potential here is 2.0 times 10 to the 3. They actually give me not the potential, but the potential difference. If the potential difference between here and here is 2.0 times 10 to the 3, then we can just as easily assume the initial potential is that value and the final potential is 0, right? The mass here is 3.0 times 10 to the 15. And we want to solve for VF here. So let's pull up the calculator again for this one. Let's say 2.6 times 10 to the minus 12 times 2,000. Let's multiply that by 2, get rid of the half. Let's divide that by 3 times 10 to the 15. And now let's square root that. We get 1.9 times 10 to the 3 meters per second. Is that good? Why do you think this charge is moving so much faster than a car would be as it goes down a hill? I mean, it's the same problem, really, right? But obviously, we're using a different equation, QV instead of MGH, and the number is quite a bit larger than the car would probably be going at the bottom of the hill. There's a couple of reasons maybe why it's going so fast. What's one? Yeah, one of them is the mass is so much smaller, right? Okay. Something is going to accelerate with a small mass, right? What's the other one? Colton? Good. Generally, electricity is stronger than gravity. And that's the big one right there, right? Generally, electricity is stronger than gravity. in almost every case. Good? This almost seems a little bit easier than the other questions, right? It shouldn't be, because the other questions, we didn't even have to bother putting in all the equations, but for whatever reason, that seems to give us trouble sometimes. Okay, these are right back to the problems that we did in Physics 20. Let's try these two problems, please. We'll make these bigger as well for those of you who are having trouble seeing that. Okay, see what we can do with these over the next few minutes, please. So after we're finished this, we're going to take a look at worksheet number 9. We're going to work on it for the rest of class, and we'll check that over on Monday. Okay, that's it for today.